Hi, this is Rob Yates, and this is the video for classwork number 3 for Unit 6, Exponential Growth and Decay. Put your first and last name up there, and what period you have math. It says exponential growth practice, it says, and refer back to your notes for the equations for the bunny populations problem, and label each graph shown with the correct bunny equation. So I'm going to remind you from yesterday, or the last time we had class, that what we called case 2, because we had case 1, the boy's request, was y equals 10 bunnies times 2 to the power of x. And then we had case 3. In case 3 were super bunnies who could have 4 bunnies in a month. And then we had case 4. And case 4 had the super duper bunnies who could have 6 per month. So, in order from case 2, it was y equals 10 times 2 to the power of x. Case 3 was y equals 2 times 4 to the power of x. And case 4 was y equals 2 times 6 to the power of x. And if you recall from our results, it was case number 4 that ended up with something like, I can't remember now, was it 3 billion or 4 billion bunnies? I believe it was 4,353,000,000 bunnies. So case 4 had the most bunnies, and what we concluded was that was because it was the starter. The starter, in fact, is the most important number when we have an exponential equation. The multiplier. I just said the starter. I meant the multiplier. The starter is not. Here's the starter for case 2. It has the biggest starter. It has 10. And you can't even compare. I think at the end of 12 months there were 40,000 bunnies for case 2, whereas case 4, which started only with 2 instead of 10 bunnies, had 4 billion because of the multiplier. The multiplier is the most important thing. So it says label each one of these graphs. Here is the y-axis. Here is the x-axis. Well, one of the things that we can use to help us detect which is that the starter number is the y-intercept. So 10 is the y-intercept for case 2, and 2 is the y-intercept for cases 3 and 4. Well, obviously this one up here is a little higher, so this must be y equals 10 times 2 to the power of x. Now we've got two curving lines that come out of 2, but one is climbing quicker, faster than the other, so that must be case 4. So this one in the middle must be y equals 2 times 6 to the power of x, which leaves for the bottom one y equals 2 times 4 to the power of x. Even though we know that this one and the bottom is eventually going to go above that one on the top, because the multiplier at 4 is higher. And if I recall, it was something like 33 million bunnies after 1 year, as opposed to 41,000 for case 2 that had 10. Question 2 says, what do these graphs look like? This is kind of an open question. You can say they look like waves. You can say they look like the sand dunes. You can say they look like my sister's hair. It's up to you. 3 says, are they increasing or decreasing? We have to look at y. Are they getting higher as we read it left to right? And the answer is yes, so they are increasing. Do they have x-intercepts? Here's the x-axis right here. Do any of those lines ever touch the x-axis? The answer is no, they do not. Do they have y-intercepts? Yeah, sure they do. As a matter of fact, we just talked about them. For case 2, the y-intercept is 0, 10. And for cases 3 and 4, the y-intercept is 0, 2. Is there a maximum value? In other words, is there ever an end to these numbers? If I keep putting numbers in for x, will it keep getting bigger and bigger? And the answer to that is yeah, it goes on forever. So there is, excuse me, I was going to write yes, it goes on forever, but the question is there a maximum value? And the answer is no. Do they have any symmetry? That is, can you put a mirror up to them, and are they the same? That is, on the left side and the right side. And the answer to that is no, they're not. Symmetry is for quadratic equations, which we're going to look at again as we get to the end of the school year, but the answer to this particular thing is no. They curve up and up and up, and they're not balanced on both sides. Which directions does the graph point? I think you know that. Are they functions? Yes, indeed. What is the domain and the range of y equals 10 times 2 to the power of x? Well, domain is the x's. And x, if you look at the graphs, it's greater than or equal to 0, but it doesn't get into any negative numbers. The range, well, that's the y's. The y's is a different case. For 10, there's our y-intercept 10, so y is greater than or equal to 10. There's no, we're talking about this top one right here now. Here's 10. There are no y's below 10. So it's greater than or equal to 10. All right, moving on. Which graph shows the fastest growth? Well, we talked a little bit about that. The one that ended up with 4 billion, what was its distinctive characteristic? If you said it had the biggest starter or the biggest value for a multiplier, then you are right. Case 4, y equals 2 times 6 to the power x, because it has the biggest starter. All right, for each table below, it says, state the relationship, if it's linear, exponential, or neither. All right, to determine if something's linear, that means it has to increase. It has to be adding either a positive or a negative number at the same constant rate each time. So, if something is exponential, that means it's multiplying, either by a number larger than 1 or by a number smaller than 1 at the same constant rate each time. We determine if something is adding an amount by subtracting the second number from the first. So, for instance, on this first one, I would say, what is 54 minus 27? And the answer to that is 27. Well, does that hold true, that pattern? What is 81 minus 54? It's also 27. So what's going on here is plus 27, plus 27, plus 27. We are increasing at a constant rate. We're adding 27 each time. So this one is linear. We could actually even say what the y equals mx plus b. I have to go back to see what y is at 0. If I go back 1, from 1 I subtract 27, it would be 0. So my